thanks for the invitation. So I have a mouthful of a talk here, but I'm mostly going to talk about image reconstruction. So you mostly using 3D scans and then you're using the images. And I'm going to try to convince you a bit that actually the way these images are created, that's kind of like the thing that you want to have in mind when you're doing general imaging. So I also, another thing to say, I have under Biguri et al. That et al is a huge ton of weight lifting here. Really a lot of people have helped in a lot of these parts of the research. Even if I'm in a math department, I will try to not have a lot of math, so please bear with me when there is a couple of slices of it. So yeah, my goal will be to convince you to think about reconstruction. So generally, you have your machine, you operate it, it gives you an image, you do things to the image. And I want to kind of like make a point that there are different ways of creating these images. There are different mathematics that actually may be interesting for you to create better images and then do better image-based modeling. I'll do a bit of math, and then I'll talk about TIGRE, which is the software that I created that provides all of this to you. Very easy to use. I think there's some users in the audience, which is really nice. So it's a way for you to, like, without knowing any of the math, just take the software and use it. And also your case studies with actually using algorithms have made a difference. There are many, but I won't go through all of them. And then so obviously you know what tomography is. I also have this, but can be CT, can be CT, and you get a sinogram, right? And then what you want to do is reconstruct it from this side. And what you generally do is you have, what the machine does, don't look at the math, that's right, but you have some mathematics, which is the radial transform, and then there is an analytic solution to this, and then you solve it, and that's what you generally all are using, which is the FDK algorithm, right? And that's what the machines produce nowadays, and that's it. But the reality is that there are other ways mathematically you can solve this, and what we generally call iterative algorithms, which is we pose the problem as an optimization problem. So this is, even if it's kind of like a typical optimization problem, but basically in this case, arithmetic say describes kind of like the X-ray. You basically given an image X that you want to reconstruct, your matrix X simulates your X-rays, and then you compare it to B, which is your sinogram, right? So everything is like, okay, I want the image that I'm trying to reconstruct that looks like, if I simulate it, that looks like the sinograms I acquired. But then one of the really good things of iterative algorithms is that you can have more things in that reconstruction, which is that J thing, and J describes prior information that you may know about the image, right? So you may not have anything, like you may know, for example, that your image is piecewise constant, right? Sometimes you take a reconstruction and it has a lot of pixel noise, but you know that this is just noise, and because you're sampling whatever additive manufacturing is, right? So it's one material, and this is actually information that you can give the algorithm so that it produces an image that doesn't have this noise, right? So this is common total variation. I think someone was talking just about total variation. So you can kind of like add this information, and there are a lot of other information that you can add to your images. So this gives them quite a lot of power, and I'll show you images. But and if you don't want to know the math, the way it works is we take an image in estimation before we compare it to the data and we update the image, and you do this iteratively until you find the solution. So why should you care? Because you're all using this algorithm, the CT scanners. You put it in, it gives you an image. It's great, right? So why care about more advanced mathematics? So FPP is great, FDK is great when you have no noise and full sampling. And if any of you operates these machines, there is a ton of effort to the noise level, the exposition, all the parameters you need to do so the image in the end looks good, right? But actually, iterative algorithms just don't care that much. I mean, they do, but they have way better performance about this, right? They perform way better when there is more noise, when your geometry is a bit weird because you cannot sample the entire circle, and so on, and then you can add this information to the algorithms. So they're better, but obviously one iteration is way slower because, one iteration requires more computation than the entire structure that you generally use, and they're very memory expensive. So, it's not everything great. So from now on, I'll show you images. This is just kind of like to make my point clear. And this is a medical case, but I will show kind of like micro CT cases later on. That's kind of like a phantom. This is what a medical scan will obtain, and these two are two different iterative algorithms, right? That one just kind of like it's a standard iterative algorithm, but it's kind of like less than image. And in this one, we actually say, oh, actually, our human is quite flat, so tissue should be more or less the same pixel value and so on. And you can see that produces like visually better image, right? I don't need to show image metrics or anything; they are better. And this is 100 projections, which is also one of the advantages of iterative algorithms, which is they perform really. They need way less data, right? So clinical scan generally is like 700 projections. If you use micro-CT, you probably use 3,000 at least. And this kind of perform better when you have very little kind of like projections because you're doing in situ experiments or because you just cannot acquire enough data for other reasons. So a lot of during my past 8 years, I've been writing this software called the TIGRE toolbox. And basically it is a toolbox, it's open source, super easy to use, MATLAB and Python. You can, load the data set with one line. In fact, again, like someone in the audience has written a data loader for X-ray scanners, but you have like, I think it supports like 5 or 6 scanners nowadays. And you have it uses GPUs, so everything is fast or as fast as you can get. And we provide about like 25 algorithms. So if you find later to some nice algorithm, probably implemented in TIGRE, so you can just like in one line use it and it will produce the nice images. So please go download it, submit issues and tell me what doesn't work so I can fix it. So now let me just show you actual examples when iterative algorithms made a difference. So I maybe don't have time to show all of them, but let's start with this very nice image, which it's a coffee bean that we scanned in Southampton. And if you can see, it's fairly big image, 3,000 by 1,000, 3,000 by 1,000 volume. You can see that the projections are really big, and actually are 2,000 projections, which is quite a lot. And it took about 45 hours to scan. So that's a SFK. This one is one of the iterative algorithms, which took about 4 hours to reconstruct, which comparing to scanning time, I think is reasonable. And in particular, this is a good example because I would argue that that's like really high quality data. And if we actually zoom in, I would argue that iterative algorithms are doing way better than your standard reconstruction. In fact, if you want to like know the porosity and you have some algorithm that segments those small holes, this image is way better than that other image, right? So you can see that the noise reduction effect is really high and so on. And this is still with like fairly good data, right? 45 hours of scan is not something that we generally can afford in a CT scan. So iterative algorithms are better, yeah. Another typical example that may happen for different reasons is that you may not be able to scan the entire circle, right? So a very typical case is laminography, where your sample has a very bad aspect ratio. So if your X-ray penetrates one direction, the long direction, then the sample is transparent in the other one. And if you penetrate the thin one, then you don't see anything in the long direction, right? So which means that you need to have some weird geometry when you like move the sample around, rotate it a bit, and whatever. You can never like kind of do 90 degrees. And this is very common for composite materials. Generally you have a big panel or something, right? And so it's something that actually industry is really, really interested in. And what happens is that your standard algorithm generally just fails miserably trying to reconstruct this, right? So we did a study, which is not that one, so I put the wrong one, but I can give it to you if you want. When we try different kind of like methods and different algorithms, and this is a lot of it, but if you look at this image in the end, you can see the cut of the profile of the sample, and you can see that in red you have like a lot of noise for the standard algorithm, huge peaks, and in blue kind of like the edge is quite perfectly, with kind of like right? So again, another example where like actually using iterative algorithms will give you something that is data-wise better. To be fair, often FDK looks better because we really get human likes very sharp images, and FDK often just enhances those images. So we sometimes go like, oh no, that looks better, but actually, qualitatively, the iterative algorithms tend to be better. Another kind of like weird thing you can do is, and that we did when I was in Southampton actually, is think about reconstructing in different spaces than just voxels. So often in additive manufacturing, you may have a CAD design that then you manufacture and then you produce, and you get a voxel image that then you may want to do image-based simulation, so you mesh it again. So we go from triangles to triangles by going through voxels. So can we just do everything in triangles? Why not, right? And the answer is yes, we can. So one of the work that I did when I was in Southampton, and again, like this can only be reconstructed iterative algorithms, is saying, okay, given a CAD model, I can make a finite element model out of this, and give my iterative algorithm reconstruct on this mesh, right? This is prior information. I know that what I'm imaging is that sample, and therefore I know that it more or less has to be like that, right? And in fact, we can reconstruct on that, and then refine the mesh, because the reason you're scanning this is because perhaps it doesn't exactly look like the one that you expected to see, right? So I did a lot of code, and I'm not going to go through it, but look, a bunny and a dragon, it works. But one of the things that we also did, as I said, is like, okay, we can reconstruct in a mesh, and then as you go reconstructing, because you're all the time comparing to your data, you can go, I know which triangles are not really doing that well, and I split them again. And I keep splitting them, and then you can have like a better finite element mesh that represents that you said that you've been scanning. So, example, that's a voxel-based reconstruction of 50 cube, which is tiny, but that's the same amount of elements as that tetrahedra, the second image, which is approximately the same amount of elements as a tetrahedra image. So it's literally from the same scan. And then what happens with that one is that obviously it has like some noise and some surfaces not properly done, and then you can like remesh that on the fly while you're reconstructing and get kind of like the sample that you image, right? And so, okay, I won't get into this, but you can see that the error of the versus your ground truth kind of like goes the same, and then you can like refine the mesh, refine the mesh, refine the mesh. So you can capture all these small things that are in your data, but a voxel may kind of limit while still keeping the area that is not interesting, like low elements. And again, this can only be done with iterative reconstruction because the kind of like your standard algorithm doesn't really work in non-voxel meshes. So kind of like not to overwhelm you a lot, but like one last one I think is relevant to those people here. This is a work that we did. I did with some people from IBSim in the Netherlands. So they were scanning some fiber reinforced polymers, and they wanted to know, like in the manufacturing process, what are the porosities and so on. And they had like several ways to test this. And their CT scan was not matching the other test. And what happens is that your CT scan looks like that in the top, and what happens is that you see a lot of black dots, which are caused by this kind of like peak that you saw in the previous image that FDK causes, right? So when you have a lot of small things together, FDK tends to like overestimate and underestimate the pixel value. And that basically, in this sample, create black dots which look like pores, and therefore their porosity estimation algorithms that they were using were like, oh, this is 15% porosity. I don't really know about porosity, but some number that is very high. And they knew it was wrong. So they just plugged in an iterative algorithm, two different ones, slightly different, but you can see that like it's very clear that the holes that should be there, that holes are there, and the ones that are not are gone, right? So suddenly their kind of like entire pipeline was fixed by just adding this thing into their reconstruction. And I think in this case it's also because the geometry was a bit weird, because again it was a bit kind of like laminography type of sample, very very wide and very thin. Have some examples for synchrotron data, which kind of like also help, and segmentation help, but I'm not going to. So finally, conclusions. So whenever you are scanning something and your scanning conditions are not perfect, so there's a lot of noise. You need to scan very fast. You cannot do it. Your geometry is not perfect. Do think about doing the reconstruction better rather than just necessarily changing a lot of other things, right? Because maybe that will actually make the difference. So it's worth having a look, having this kind of like tool in your tool set of imaging scientists. There are a lot of approaches for reconstruction, which is why I provide 25 algorithms. I'm not, a lot of people ask me, which is the best algorithm? There is no answer because algorithms are kind of like similar to the problem that you're trying to solve. So you kind of need to know. Then you can use TIGRE for all of this. So open source, free to use, including industrial purposes. So please download it and give it a go if it's something that you want. And finally, yeah, take home message, do not ignore reconstruction when you're in city. So a lot of people help me do this, and a lot of institutions. But if you have any questions.